Hello, grade 11 chemistry. My name's Mr. Boudreau, and this is our first lesson. Just a few things about these YouTube videos. There's going to be a couple of useful things that I'm going to keep on screen at all times. The first one is up here is going to be a keep in mind. So that's just going to kind of be a helpful guiding principle for whatever part of the lesson we're talking about. Here are the learning goals. Those aren't going to be on all the time because they cover a lot of the screen, but I'm going to talk about them at the start of every lesson. And every time we move to a new learning goal, I'm going to change the keep in mind. And to support that, down here is going to be the current topic. So the current topic, that way you can look at it and see, oh yeah, this is why he's going off on this tangent or whatever he's talking about. So this is our first lesson, so I figured we'd start with a quick introduction to the course. This course has 5 units. The first one is atoms and bonding, so almost a rehash of grade 9 chemistry with a few extra things involved. In grade 9 chemistry, you guys would have talked about stuff like ionic and molecular compounds, naming ionic and molecular compounds, the difference between acids and bases, and things like that. This unit has a lot of the same content, but with a little bit more complexity to it. The second unit is chemical reactions. Chemical reactions, very much a rehash of grade 10 chemistry. We'll talk about synthesis reactions, decomposition reactions, single and double displacement. But then we go a little bit deeper. We talk about combustion reactions. We talk about special synthesis reactions and special decomposition reactions, patterns that chemists have found within synthesis and decomposition reactions. Then we get to the real meat of the course. This is the newer stuff, quantities and chemical reactions. There's math involved. A lot of students find it to be a bit of an interesting transition because there's, suddenly we're actually working with amounts of chemical. So that's the part of the course where we really move away from what you've done before and start in on new stuff. And then that math trend continues through solutions and solubility, where we do the same kind of math but for liquids, for solutions, and then atmospheric chemistry, where we do the same kind of math for gases using pressures. Solutions and solubility also includes a lot of acid-base work, and atmospheric chemistry includes stuff like the composition of the atmosphere and gas phase reactions. What is the gas phase? Things like that. So let's just jump into it. 2 questions real quick. What is chemistry and what is a chemical? Take a minute to think about it. Maybe pause the video. Maybe the second question might be more interesting than the first. What is a chemical? Well, everything's a chemical, right? Any object. This is some kind of plastic. It's a chemical. This is maybe a different kind of plastic. That's a different kind of chemical. My skin is made out of chemicals, right? My teeth are made out of a different chemical. Everything is a chemical. Any physical object, even things we can't see, like the air, that's made out of chemicals. So what is chemistry? What makes chemistry different from, say, physics? If a chemical is any physical object, or if any physical object is made out of chemicals, how does chemistry differ from physics, and how does that differ from biology? Well, at high levels, there's not really much of a difference. They kind of bleed into each other, but I guess in high school, chemistry is kind of that middle ground between the very big and the very small. In physics, we talk about these macro phenomena, stuff like things moving, how do we add math? How do we model that movement? These are kind of more abstract concepts. And in chemistry, we get down into, what is this thing that's moving? How do we change that thing? It's more, it's less abstract, less mathematically modeled, and a lot more to do with empiricism, a lot more measuring, things like that. So a lot of the rules of chemistry are really just guidelines that we've developed over years and years and years of experimentation. Yeah. So I guess chemistry loosely is a series of I don't know, a series of models of how matter interacts with other matter, um, based mostly on empirical observation, based mostly on experiments, rather than mathematical modeling. Yeah, okay. Let's do a brief history of chemistry. I'm going to move my thing down at the corner. It's an FYI. This stuff isn't actually part of the curriculum, but I find it's important to kind of talk about the human relationship with chemistry and how it's evolved over time, just as a little introduction to the course. So probably the earliest chemistry was from the Bronze Age, using fire to purify metals. You find a rock with some copper trapped in it, you can heat up the rock, the copper will turn into a liquid and leave the rock. Meanwhile, the rock will stick around. You can get rid of the impurities. The Egyptians did a bunch of that stuff. You got this nice gold extractions on their sarcophaguses and things like that. Then you got the ancient philosophers like Aristotle. They tried to explain phenomena using a small number of elements. You might have heard of the four elements: air, fire, water, and earth. They actually had a more involved system than that. Each element had properties. The properties were hotness versus coldness and wetness versus dryness, and they had this model that they would interact in different ways. That fire had some air in it, and that's why it rose, and water had some earth in it, that's why it stayed near the ground. Unless you got the water hot, where it became, it turned into steam, which is kind of like water with some air and fire in it. They had these interesting ideas. It was the first concept of kind of defining matter as a collection of individual things, instead of paper is just paper, and there's nothing in common between paper and plastic, where we know now that both have carbon in them. Stuff like that. Alchemists really got into this element thing, and they started extracting individual elements. They were really interested in actually changing different things from one thing to the other, and they started purifying individual elements for the purposes of study rather than to use them. We were purifying individual elements back in the Iron Age, essentially. But the alchemists were more interested in their properties, in getting very, very, very pure things that they could then study. They made a lot of glassware. They started making, flasks and beakers and things like that. A lot of our chemistry apparatus that we use now come from these alchemists. So they started bringing almost a kind of scientific method to it. They had recipes, they had ratios of things. Then we get into the actual foundation of modern chemistry, where Francis Bacon, here's a picture of him, he's the guy that said knowledge is power. He popularized the scientific method. So this idea of do an experiment, then change one thing, and then do the experiment again, and that one thing you changed is the thing that must have affected whatever your outcome is. At the same time, there was a wave of rationalism that was sweeping through Europe, and Europeans start discovering a lot of elements and laws because they're kind of the dominant world scientific power at the time. A lot of this stuff was also being done in China and also being done in the Arab world, but a lot of the stuff that we talk about is named after Europeans, so that's kind of how it works. Later in the course, we'll learn a lot about these guys, especially the ones that were working with gases. When we talk about the gas laws, we will get into a lot of these meteorologists, and particularly hot air balloon enthusiasts, because they were really into chemistry for some reason. All right, Dalton. Dalton was a meteorologist in the 1800s. Again, one of the guys that worked with gases. We're going to see him again in our last unit in gas phase chemistry. And he was kind of credited with the creation of atomic theory, because gases were very easy to trap and measure volumes and pressures of. It was harder to get an accurate an accurate look at, say, the concentration of a liquid or anything like that. Gases were much easier to combine in exact numbers. So from working with gases, Dalton came up with this atomic theory of matter, that elements are made up of extremely small particles called atoms. You guys probably know this. Atom actually comes from the Greek, from this guy Democritus, who said that, well, essentially his whole thing was, this is paper, and then I can rip it in half, and now I've got two things, but they're still paper, and I rip that in half, and then that's still paper, and that's still paper, and that's still paper. And then Democritus said that at some point there's going to be a smallest piece that I can't rip in half anymore, but it's still paper. That was Democritus's idea, and he called that smallest piece an atom, and from the Greek atomos, which means indivisible. And Dalton took the same word, atomos, for atom, for indivisible. Of course, now we know they are divisible, but yeah. Atoms of a given element are identical in size, mass, and other properties. So he said, hydrogen is hydrogen is hydrogen. It'll always react like hydrogen. It'll always have the same mass as other hydrogens and stuff like that. Because he was working with gases, so he had, I have this balloon of hydrogen. I have a different balloon also of hydrogen. These two balloons are going to do exactly the same thing, no matter what. Which is, pretty much accurate. We're going to see when we talk about isotopes that it's not exactly true, but, credit where it's due. This is the 1800s. Atoms could not be subdivided, created, or destroyed. Well, back in those days, that was true. Much later, in the mid-1900s, or I guess earlier, a bit earlier than that, they started subdividing and creating, destroying atoms. Probably around, 1899, when Becquerel discovered radiation. That was the first hint that atoms could change form. Atoms combine in simple whole number ratios to form chemical compounds. Yes, that one is actually absolutely true. Water is always H2O, 2 hydrogens, 1 oxygen. That was Dalton's big thing. And then the last piece is chemical reactions. Atoms are combined, separated, rearranged. They don't pop in out of nowhere. Hydrogen and oxygen make water. The water still has hydrogen and oxygen in it. That was Dalton's big deal. So that's why we care about Dalton as far as a chemical theory. We still use this back from the 1800s. We still use the notation of like H2O, and we still say H2 plus O2 becomes H2O, and things like that. It's very useful. All right. So now we're into our next piece, which is models of the atom. So I'm going to pause, but first, draw me a diagram of an atom. Just put it in your head, whatever atom you want, draw me a diagram. See what you remember from grade 9. I'm going to pause and change this stuff. Okay, we're back off pause. So the prompt was draw an atom, draw me a diagram of an atom, or just have one in your head. And chances are you might have something in your head that looks like this. I like to call it the Jimmy Neutron model of the atom, because it's kind of what the Jimmy Neutron intro looks like. Something like this. Even the Encyclopedia Britannica's got this kind of thing going on. The thing to know is that that's actually wrong. It's absolutely 100% wrong, and yet it's the model of the atom that kind of people have in their heads. Because it's so evocative, right? It looks like a little sun with planets going around it. It's really very cool. And a lot of them have, for some reason, 3 electrons going around them. And the 3 electrons, the kind of hexagon looking thing, is a very, very popular motif for atoms. And I'm not sure why. I guess it looks pretty. But that's wrong. That is absolutely fundamentally wrong. This is a little bit better. Right? Here, I'm going to move my my thing out of the way. This is a little bit better. And, you know, it's the Borh-Rutherford model. This is pretty good too. You know, this is even better than that, but even that is wrong. So, you know, models of the atom are inherently wrong. The reason that they're inherently wrong is that they are models. Right? A model is a model. It doesn't represent reality, absolute reality. It represents reality, you know, in a simplified way that lets us make predictions. Right? You know, there's a lot of talk about modeling these days with the current coronavirus, and those models are useful, but every single one of them has at least a little bit of error. The same thing for all of these atomic models. So, you know, each one had some kind of predictive power. Each one has more predictive power. We're going to top out at the Borh-Rutherford models. We're going to stop here. This is grade 12 concept type stuff, the quantum model of the atom. But we stop here because it's predictive for chemical reactions, for most chemical reactions. The quantum model is more predictive for certain other things like radioactive decay and things like that, and shapes, especially molecular shapes. This is much more predictive, but this works really, really well and is a simple enough model for us to work with. So just jumping through these very quickly, Dalton said, well, we just talked about Dalton. He said everything is made up of little particles called atoms that are indivisible. So indivisible means that hydrogen just looks like this in Dalton's mind. It's just a ball, and somehow it knows that it's hydrogen. Thomson came along 100 years later and discovered the electron. And so he realized that you could take this electron and rip it off of an atom and leave behind an ion, and that turned into the Thomson model, where there's a positive charge with negative charge distributed equally inside it. Then along came Rutherford, Ernest Rutherford, who gave us, you know, the Rutherford model, the one that everyone somehow gets in their head when they think about atoms. When they want to diagram an atom, everyone goes with Rutherford, even though it got improved 2 years later, but this is just nicer looking. Rutherford proved that the nucleus is very, very small, and in the center with a bunch of empty space, and then the electrons around the outside. You might have heard about his gold foil experiment. This was actually done by his students. One of his students was Geiger, the guy who invented the Geiger counter, and in fact that experiment, Geiger inventing the apparatus for Rutherford's experiment, was the first kind of Geiger counter. It led pretty much directly to Geiger inventing the Geiger counter. So Geiger was a PhD. He had a PhD in chemistry. He was working under Rutherford in the same laboratory, and there was this other guy whose name I actually don't remember. He was an undergrad that was also part of that team. So Geiger and it starts with an M. I forget what his name is, but Geiger and the other guy, the undergrad student, actually did the gold foil experiment, and then Rutherford just mathed it out and proved that it's like this and not like this. Essentially, the alpha particles would come in, and a small fraction of them would bounce would bounce off. Alpha particles are positively charged, and they would get repelled by the positive nucleus. Thomson explained it as lots and lots of individual atoms, and it would bounce off the individual atoms and slowly kind of get deflected. But Rutherford proved with math, with basically trigonometry, that all it took is one atom to get these big deflections, and with one atom the probability of deflection exactly matches what they observed, compared to what the Thomson model predicted. So Rutherford didn't actually do the experiment, but he did all the math and did the paper. So yeah. Now Rutherford had this other student called Niels Bohr, and Niels Bohr had a foundation in electromagnetics, Rutherford said that they can't be orbiting, that the electrons can't be actually orbiting, because any time that a charge is accelerated, it releases energy, and moving in a circle is constant acceleration. So they would constantly lose energy, and then they would fall in, and the whole atom would just kind of stop looking like this, even though atoms seem to constantly look like this. So Bohr said that it seems like the electrons are locked into specific energy levels, and they can't leave those energy levels, and that's what keeps them at specific distances. The proof of that was from something called spectroscopy, which is a grade 12 concept. So, take grade 12 chemistry if you want to learn more about that, or just look at my grade 12 video about that. And then, another 13 years later, Schrödinger, you might have heard of Schrödinger with Schrödinger's cat, he created this equation for different particles, and it described very well the same kind of energy levels that Niels Bohr had predicted and had seen with his spectroscopy experiments. And it suggested that the electrons are actually in this cloud of probability, and they don't actually exist in one specific place at one specific time. They just form this cloud of probability around the nucleus, the shape, the size can be determined mathematically. We don't get into that. Not in grade 11. We stop at Niels Bohr here and his energy levels. So, yeah, it's wrong. It's fundamentally wrong. Electrons aren't individual points, aren't individual particles. They have a mass, but they don't really have a volume or anything like that. And they don't sit in nice circular orbits. It's not just the shells, there's also subshells and stuff like that. But we're going to stick with this model because it's nice. It's a good level of complexity to explain chemical reactions, which is what we're interested in. So let's look at it. Hey, look, it's the wrong model of the atom. It's extra wrong because there's 4 electrons in an orbit for some reason. It doesn't matter. What's important about this is the subatomic particles, which is what we're trying to review next. So I'm going to pause, and we're going to get into subatomic particle review. Okay, we're back off pause, and we're reviewing subatomic particles now. Take away those learning goals. One thing to keep in mind here is electrons are comparatively very, very, very far from the nucleus, and they're there in a sort of cloud. Probably the easiest example to think about just how far away the electrons are from the nucleus and how much empty space is in the atom is I took a gold nucleus as an example, and I did some math. I worked out that the electron is approximately 9,000 nucleuses away from the nucleus. So you've got the nucleus, then 9,000 nucleuses worth of empty space, and then the outermost electrons. So it's the outermost electrons, but in that case, it's like, if the electron was on the end of my arm, the nucleus would be the width of one of my hairs. It's an incredible amount of empty space. That's, of course, the outside electron. The inside electrons are a little bit closer in, but the distance is still comparable. Maybe the nucleus will be 3 or 4 of my hairs, but it's still a huge amount of empty space. It's incredible. I'm going to move my stuff over to the side here. Okay, so here's the atom. You got neutrons and protons in the center. You've got electrons around the outside. The electrons form this kind of cloud way out to the outside. The nucleus is really, really, really comparatively tiny in the center compared to the size of the cloud itself. But the nucleus has almost all of the mass. If we look at the masses, a proton is, in terms of AMU, about 1. A neutron's about 1 AMU. Electron is 0.005. So that means it's, 1/2000th the mass of a proton or a neutron. 2,000 electrons would give you the mass of a neutron or a proton. And the heaviest element we know has, 118 electrons, 118. So it doesn't even come close to that 2000 number. Even the heaviest, the element with the most electrons, the electrons are not contributing a lot to the atomic mass. It's all protons and neutrons. Protons are positive, electrons are negative. Interestingly, even in Rutherford's studies, in his work, they didn't know that the proton was a thing yet. They called it positive electrons, which are also a thing. They're called positrons, but they're completely different. Rutherford actually believed that the nucleus had electrons and positive electrons together in the center rather than any kind of neutral thing. He used that to explain the extra mass that he saw in his studies. The neutron wasn't discovered until like the 1930s by Chadwick, I think. So the neutron has about the same mass as the proton, a little bit more, but zero charge. It contributes to mass but doesn't contribute to charge, and it's in the nucleus. So hopefully you guys remember this from grade 9. Quick little, math thing. How many protons, neutrons, and electrons does xenon have? A quick little thing. Here's xenon on the periodic table. This is its mass number. This is its atomic number. So mass number and atomic number. And we can use that information to figure out, that information and this information to figure out how many of each subatomic particle it has. So I'm going to, pause and go over to my my whiteboard, and I'll see you over there in a second. Okay, so I'm back off pause, and we're on the whiteboard here. We're going to talk about how many protons, electrons, and neutrons. So how many protons, neutrons, and electrons does xenon have? And all we get is the atomic number and the mass number, and this concept of a nucleus in the center and electrons going around the outside. And we can use the Jimmy Neutron model here. We can use the classic Rutherford model because it doesn't really matter. So positives are on the inside, so protons and neutrons are on the inside, and the electrons are on the outside. What's important to note is the atomic number is literally just the number of protons. So number of protons is easy. The periodic table is arranged by how many protons the atoms have. So the atomic number is just how many protons it has. So the atomic number is number of protons. So we already have our number of protons. There's 54 of them. 54 protons. 54 protons. How about the number of electrons? Well, for the electrons, a neutral atom, remember that the atom is neutral. That the atom is neutral. The only way to be neutral is to have the same number of positives as negatives. Therefore, there's 54 positives equals 54 negatives. There have to be 54 negatives. Therefore, in a neutral xenon atom, there's 54 electrons. 54 electrons. So, 54 of those. Making up the shells. And then there's the neutron number. Right? The neutron number. So both the number of protons and the electrons come from the atomic number when you're talking about a neutral atom. For neutrons, that's where we're going to the mass number. Right? Remember what I talked about just a second ago, that the electrons are 1/2000th the mass of 1/2000th the mass of a proton or a neutron. One electron, or actually all 54 electrons together, would change, that number, because each one is 1/2000th of an atomic mass unit. So, all 54 of them together change that number, maybe a little, actually they would change kind of these two numbers, right? Those two numbers. They don't affect the big number very much. So, you know, the electrons are kind of there. So the rest of this, mostly that guy, that's all protons and neutrons, really. Right, even down to here is all protons and neutrons. So kind of, we take that 131, we kind of round it, is the number of protons plus the number of neutrons. Those neutrons. We know that number of protons is 54, so you know, easy enough, the number of neutrons is going to be 131 minus 54, which is, what, 27? No, not 27, 27 plus 50, right? So 77, is that right? I don't need a calculator. Yeah, it's been a while since I've done math. 131 minus 54. Yeah, 77. I had that right. 77 neutrons. So this is a little review of atomic numbers, of atomic theory, right? Of this kind of stuff, the subatomic particles. You might wonder, you know, where does that 0.2 come from? Where does that 0.9 come from? That's from isotopes. We're going to talk about isotopes later in this unit. Basically, you can have different numbers of neutrons, and this is a running average of how many neutrons you have. All right, next piece was reviewing Borh-Rutherford diagrams, reviewing of Borh-Rutherford diagrams. So I'm going to pause and set that up for you. So here's a Borh-Rutherford diagram. Here's the electron shells. They go 2, 8, 8, 18, 18, 32, 32. There is a pattern there. It's actually just the square numbers. So 1, 4, 9, 16, right? 1, 4, 9, 16 times 2. So 2, 8, 18, 32. You know, there's reasons for that, but that's grade 12 chemistry stuff. So that's a Borh-Rutherford diagram. Here's what they look like. Take away that. There's 2 in the first shell. There would be 8 in this shell, but carbon only has 6 protons, so there's 6 electrons to put in. So, you know, the 4 in this shell is it. Electron shells are important. You know, it's the first shell has 2, second shell has 8, third shell has 8, then 18, 18, and then 32, 32. Too much to really talk about. But there is this shortcut, which is called Lewis diagrams. So, you know, these are better. So let's look at carbon here. Here's carbon. There's 4 dots around it. What do you think those 4 dots are? Well, they're actually, gotta go back. Actually, those 4 electrons, 1, 2, 3, 4. So those are Lewis diagrams. I should probably change my my thing then. Let's change this to Lewis diagrams. Right, Lewis diagrams. So 4 for carbon, 3 for aluminum. If you look at the periodic table, aluminum, and you do the Borh-Rutherford diagram, you'll see that it's got 3 on the outside. Sulfur has 6. Electrons like to pair up. That's how they make bonds. So we make them pair up in the Lewis diagram as well. And radon has, you know, 8 on the outside shell, and so we put 8 out there. Yeah, they're useful for predicting compounds and reactions. They're much easier to make because you just put the symbol instead of saying how many protons and neutrons you have. The reason that we can do that is because, you know, any chemist with their salt can grab this and figure out how many neutrons and protons you have. We just did that over on the whiteboard. You know, we were able to do that. So if I give you, say, sulfur, you can go over to your whiteboard and you know, do the same kind of thing and be like, hey, I know exactly how many neutrons and protons and electrons it has. No big deal. So, you know, Lewis was like, yeah, it's fine. Every chemist knows how to do that. We'll just get rid of that. We'll just put the symbol in there because everyone's got a table now. But the outside electrons are important. Right? They're easy to make. They're a model of what's going on, but they're good enough for predictions. Remember, all models are wrong. Some models are useful. So, atoms. Every atom is surrounded by these electron shells. And the shells means the outside of the atom is negative. right? And negatives repel. So remember, like my analogy is that if the nucleus is like a couple of my hairs thick, the atom is at the end of my arm, or the electron's at the end of my arm, the negative charge. So there's a bubble of electric charge around the atom, much, 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 much bigger than the size of the nucleus. The nucleus still has, effect, still pulling on those negative electrons, but when two atoms get near each other, those negative electrons are going to feel each other, and they're going to go away from each other, like two balloons hitting each other kind of thing, right? So that's why the outermost shell is so important. We call it the valence shell, from Latin. The valence shell is the outside shell. And here's some Borh-Rutherford diagrams. You can see that, 1, 1, 1 in this entire row, 2, 2, 2 this row, 3, 3, 3 this row, 4, 4, 4 this row. And if you remember from your grade 9 chemistry, all of these ones explode with water. All of these ones are reactive poisonous gases. They have similar properties based on how many electrons are in the outside shell. These ones are all noble gases. They don't react. So the outside shell is the most important thing. So those are valence electrons. Right? And this is kind of a diagram of what I'm talking about. It's the cloud of electrons around the nucleus. Of course, if we wanted to do this properly, the cloud should be way bigger, the nucleus should be way smaller, and you just wouldn't be able to see the nucleus at that scale. Elements only feel the outside electrons. To draw a Lewis diagram, it's pretty straightforward. You just have to draw how many outside electrons there are. So for aluminum, it would be very simple, right? It would look something like this. Aluminum has 1, 2, 3 valence electrons. 1, 2, 3 valence electrons. And that's the entire diagram. We don't need to think about how many neutrons. We don't need to think about how many shells underneath there are. There's even better shortcuts to this, right? Because this is what the shells actually look like. This is what the bubbles of electrons actually look like. And if you look at these guys in the middle here and these guys down here, they're kind of weird looking, and they're actually small. They're smaller than these guys, these big shells out here. And so they kind of hide underneath these two shells. And so really only these two make the big outside shells that other atoms are going to see. And this corresponds to the transition metals and the F block elements, the lanthanides and the actinides. So, they have weird shapes. They're lists of their number of valence electrons. This is where you get stuff like copper 1 and copper 2, iron 2 and iron 3, stuff like that. But generally, we can ignore them when we're figuring out the Lewis structures of these elements. So we just draw the valence electrons. We ignore the transition metals. Those are the transition metals, right? That block that's underneath the table and the big block under the bottom. We just ignore them. And, this one always has 1. This row always has 2. This column always has 3. This column has 4. This column has 5. This column has 6, 7. And that column always has 8 or 0, depending on how you want to think about it. Helium's the only exception. It's got 2 valence. So I'm going to bring my stuff over here. Helium's only got 2 valence. But the rest of them have 8. So there's this really, really nice shortcut to drawing Lewis structures for your atoms. So Lewis diagrams, they're used for those groups and those groups. Everyone here has 1, everyone here has 2, everyone here has 3, everyone here has 4, 5, 6, 7, 8. According to Borh-Rutherford, these guys all have, this krypton should have 18 in its valence shell. And the xenon should have 18, and the radon should have 32 in its valence shell. But because these guys have those little small kind of shielded bubbles, they end up being overridden by the 8 electrons that fit into these shells. So if we go back to this, notice that radon here, the Lewis structure just has 8 electrons, even though we know on the table that it should have 32. Yeah. And that's the end of the lesson. Thanks for paying attention. That's 40 minutes, really good timing, and I'll see you guys in class.